Hello and welcome back to our linear algebra series. In this video, we will be discussing norms, inner products, and dot products. So, let's start off with norms. What is a norm? So, in the last video, we talked about vectors and how we can just represent a vector as just a line. We can show this is coming from the origin and denote it with this little symbol over here, and any letter. I just chose V for vector, and we will define this vector with a set of coordinates. So we can put anything here. We will put V1 and not X, V2. So this is the vector. And so this brings the concept of norm. What is a norm? We denote norm first using this symbol or notation where it's like absolute value brackets. So the norm you could think of as the length of a vector. So this length that we're measuring over here, the length of this line is going to be our norm. How do we calculate this norm? If you think about it, in R2, how would we calculate norm? Then the words I'm using may sound a little complicated because you may not be familiar with them yet, but it's actually a pretty easy task. We've probably done this many times in our mathematical careers. So this is none other than just Pythagorean theorem. So let's say A, B, C. If we want the length of this vector, which is C, all we need to do is find A squared plus B squared, and then take the square root of this, which is equal to C. This is going to be positive, and we're just looking for length, which is going to be a positive value. So there are also some properties associated with norm. So to more formally define norm, we can say that given a vector space, so let's say definition norm, so say V is equal to Rn, so an arbitrary space, and we'll be working with the reals, a set of real number. So we can say that the function, say f, maps this space to just the set of reals. So the properties associated with norm are, there's first the additive property or inequality. We have P, we have two arbitrary vectors, x and y. This is going to be less than or equal to P of x plus P of y. And then we'll just state for all these properties for all x and y belonging to this space, or Rn. Our second property is P and some scalar, so let's put alpha times x is equal to the absolute value of this scalar times p of x for all x and where alpha belongs to real. And our third property is if x equals 0, then p of x equals 0. And this actually goes both ways. So it's if and only if x is 0, then p of x is equal to 0. Again, p is just representing the norm. Then we have p of x is greater than equal to 0 for all x in this space. So we can, but as you see, we actually use norm for our n. This example, we only showed norm for our 2. But how do we extend this? So we can extend this fairly easily, like you may have seen in the 3-dimensional space. It can just be, we'll start using, instead of a, b, c, we'll use just x. So we'll have x1 plus x2 plus x3, and these are all squared. So this is basically the length of that vector, and it can be extended to any arbitrary number of x's. x1 plus x2 plus x3, x3 plus all the way up to xn squared, and we take the square root of this to find our norm. And these properties apply. So now we'll move to the dot product. Dot product. So as you've seen with norm, this is not necessarily linear. To interject linearity, there is the dot product. So the dot product, basically, it also has a set of rules. It works like this. So we have two vectors. Say we have v and u, where we define v as v1, v2, all the way up to vn, and we have u, where it's u1, u2, all the way up to un. So the dot product of these vectors, and we can say that all v, like I, belongs to real for all I, and we can say I, natural numbers. And same thing for u. So the dot product of these two would just be, we would define as v1 times u1. Let's have dot u, just be v1 times u1 plus v2 u2 plus all the way up to our arbitrary n, which is Vn Un. We can define this in sigma notation as sigma up to n, starting at an I that defined as 1. We could have Vi Ui, and then it just takes a sum of this product for all i's up to n. So the dot product also has some associated properties. We have as you can see, the dot product basically is a function that maps the vector space V, like an arbitrary vector space, to V times V, which just maps it to a real number, where V can be some Rn. So our first property is V dot V is greater than equal to 0. So let's prove this actually. It's pretty simple if you think about it. So I'll give you a minute if you would like to pause the video. Okay. So V times V. We know that if we want to dot V with itself, all we are essentially doing is V dot V is equal to V1 times V1 plus V2 times V2 all the way up to Vn times Vn. And it's pretty simple to see. It's just a V squared then. V2 squared plus dot 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 Vn squared. So we know if we square a number, it must give us a non-negative product. So if all of these are non-negative, then it must be greater than equal to 0. We're summing all these non-negative products. So we know that the lower bound would be 0, meaning the lowest these could possibly be would be 0. Again, pretty simple to see. If we draw a quadratic, we know the lowest that it could be would be 0. So just like that, the lower bound for each of these would be 0, and then the lower bound general of this would be 0. The second property is that if V dot V is equal to 0, we want to show that V is equal to 0. This is pretty similar to the one above. So you can pause the video if you want to try it again. But I'll do it. So again, what does it mean if the vector is equal to 0? That means all of the characteristics of the vector are equal to 0. 0, 0, 0, and then 0. So we want to show if we have this with V dot V, then we have this. So let's prove this. We have V dot V is equal to 0. So V dot V, again, as we did above, is just equal to v1 squared plus v2 squared plus dot 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 all the way up to vn squared. So if this product is equal to 0 and all of these are non-negative, then again they all must sum to 0. Since there's no positive numbers that this could be, they could only be positive numbers actually. There's no negative numbers that this could be. Nothing will cancel out. So it must only be positive or 0. So if any of these was non-zero, then we could not have a 0 product, and thus the property holds. The third property is commutativity. We have v dot u is equal to u dot v. So again, this is pretty easy if you want to try it yourself. We know, let's split this up into left side and right side. Left side, we will have v dot u. So this is equal to v1 u1 plus v2 u2 all the way up to vn un. And the right side is going to be equal to u dot v, which is just equal to u1 v1 plus u2 v2 all the way up to un vn. And we know that regular multiplication, since these are real numbers, is going to be commutative. And if you don't, if you need a refresh on what commutative means, it's basically saying that 3 times 2 is the same thing as 2 times 3. Some arbitrary numbers, x, y, which will say x and y are both real numbers. This is the same thing as yx. So we know that since regular multiplication is commutative and these are just reals, we know that every single one of these pairs is going to be equal, thus making this property hold. Okay, and so we should now move to inner product. Inner product is pretty similar, but the notation is a bit different. So inner product basically is a function that takes each ordered pair of elements and has the following properties. So for inner product, we have for reals, we're going to denote it with these brackets. So it's basically v times v, where v is, again, v is equal to Rn, is mapped to real. So we'll have properties where for all x belongs to this space, then x, the inner product of x and x, is greater than or equal to 0. And second property is, again, these are pretty similar to just the dot product properties, because especially for real numbers, they are almost identical. For complex numbers, it differs a bit. So we know that the inner product of x and x is going to be equal to 0 if and only if x is equal to 0. And again, 3, we know that we have the property for all x and y, which are vectors that belong to this vector space. We have the vector x and the vector y are equal to the vector y, the vector x. And the fourth one, which is for all x, y, and z that are in this vector space. And we have some r that belongs to real numbers. This property is quite interesting because we often do not think of splitting products up like this, but the inner product is actually a bilinear map. So there's some differences, and this might look non-traditional, but we have x, y, and so we have a product r times z. This splits up into x, y, plus r and xc. You may be thinking, what kind of witchcraft is this? We actually did two things at once, where we took out this scalar and we split the vectors. So if we just wanted to work with scalars, it would be x, y, or ry is just equal to r, x, y. If we had r, x, r, y, then we would have r squared x, y, where we can bring the product out. So if you have a bilinear map with these properties, you can classify it as an inner product for the space.